Hello everyone, today we are going to explain that resonance of benzene. The oscillating double bonds in the benzene ring are explained with the help of resonance structure as per valency bond theory. All the carbon atoms in the benzene ring are sp2 hybridized. One of the two sp2 hybridized orbitals of one atom overlap with the sp2 orbitals of adjacent carbon atom forming 6 C bond C sigma bonds. Other left sp2 hybridized orbital combined with the orbital of hydrogen to form 6 C bond H sigma bonds. Remaining unhybridized p orbital of carbon atom form pi bonds with the adjacent carbon atom by lateral overlap. This explains an equal possibility for the formation of C1, C2 single bond, C3, C4 bond, C5, C6 pi bonds, or C2, C3, C4, C5, and C6, C1 pi bond. The third hybrid structure is represented by inserting a circle in the ring as shown below in the figure. Hence, it explains the formation of two resonance structures proposed by Kekulé. These two structures, these both are a resonance structure, and the final structure, this is known as your resonance hybrid. Recall that resonance has another important feature. When resonance is involved, the real structure is more stable than we would expect from any other structure. We write using the one line double bond, two electron symbolized. That means one line is equal to, it indicate that this containing two electrons. This extra lowering of energy, which for benzene is about 1/3 as much as making a typical covalent bond, is quite important in the reaction of benzene and other aromatic compounds. As we will see, reactions of the benzene ring almost always result in the products which in which the benzene ring persists an outcome of its stability. When resonance theory was first applied to understanding the structure of benzene, the key feature seemed to be a resonance hybrid of ring structure containing alternating single and double bond. This immediately lead to attempt to make and study compounds like cycloocta, tetrane and cyclobutane. This compound also have a ring structure with alternating single and double bond. Cyclotetra Cyclooctatrene has been made, but it does not possess the property of extra stability and resistance to addition reaction, which distinguish aromatic compound. It readily added bromine. For example, cyclooctatrene, when treated with bromine, it will give that dibromocyclooctatrene. And then another example, cyclobutadiene, both compound having that double bond, and this compound are maybe aromatic compound or may not be if it satisfies the Huckel rule. Cyclobutadiene is extremely unstable. One cyclobutadiene molecule reacts with another cyclobutadiene molecule instantly, even at very low temperature. So it certainly does not act like an aromatic molecule, and it has been called anti-aromatic as a result. It seems that there is more to being aromatic than simply a ring with alternating single and double bonds. After considering considerable development of the underlying theory, the pattern which has emerged is that aromatic characteristics are only expected when there is a ring of pi electron in which the number of pi electron is equal to the 4n plus 2, where n is an integer, that is 0, 1, 2, 3, etc. This is known as Huckel Rule after its discovery. We can check this against the compound we have considered so far. Benzene has 6 pi electron, 2 for each pi bond, which is the number we get from 4n plus 2 if n equal to 1. Cyclooctatetraene has 8 pi electrons and there is a no integer n, which will make 4n plus 2 equal to 8. Cyclobutadiene has 4 pi electrons and also does not fit 4n plus 2. There are many other examples which support Huckel rule. It is important to be sure that the ring of alternating single and double bonds is complete. If there is an sp3 hybridized carbon in the ring, the condition for aromatic character are not present and we do not worry about checking for 4n plus 2. Here's an example. Cycloheptatrene, not a aromatic compound. It does not follow the Huckel rule. And benzene is the aromatic compound as because it follows the Huckel rule due to the presence of pi electron. Another way to see this is to look at the p orbital which combine to make the pi bonds. If this p orbital combine to form an uninterrupted ring, as is the case in benzene, then we can go ahead to use Huckel rule to check for proper number of pi electrons for aromatic character. If the ring of p orbital is broken by CH2 group or another tetrahedral carbon with no pi or p orbital, then the compound cannot be aromatic and we need not try to apply Huckel rule. Two examples are furan and pyrrole, in which 2 of the 6 electrons needed come formally from unshared electron pair on oxygen. Such an unshared pair can also come for carbon atom, which will have to have a negative charge. An example of this is the Cyclo Pentadiene Ion, which can be made by treating cyclopentadiene with a moderately strong base. Cyclopentadiene ion is sufficiently established by its aromatic character that cyclopentadiene has a pK value 16 close to that of water, that pK value for water 14 at 25 degrees centigrade. Some biochemistry text, however, the pK of water at 25 degrees centigrade is listed at 15.7. Cyclopentadiene is a remarkably strong acid for a hydrocarbon because its conjugate base has the extra stability of an aromatic compound. Ordinarily stable cation can also be made if their structure are aromatic. Here are two compounds, cycloproponium ion. They are having 2 pi electron, that is 4n plus 2 equal to 2 when n equal to 0, and cycloheptatrinium ion. They are having also 6 pi electron. If we apply that Huckel rule, that means 4n plus 2 equal to 6 where n equal to 1. Notice that here the formally positively charged carbon atom are sp2 hybridized and have an empty p orbital which completes the cyclic arrangement of p orbitals. Thank you.